Dear students, welcome to this digital lecture series. The topic of today's discussion is quantum mechanics, and in that we are going to see Compton effect. We have seen previously that when a beam of monochromatic X-rays is incident on the target material of light elements like carbon, then the scattered radiation consists of two intensity peaks. One peak corresponds to the incident wavelength or the unmodified wavelength lambda, while the other peak corresponds to the modified or the increased wavelength lambda dash. And this effect was called Compton effect. The difference in wavelength delta lambda is equal to lambda dash minus lambda is called Compton shift, and it was found that the Compton shift depends only on the angle of scattering. It is independent of incident wavelength and independent of the nature of scattering material. So if a graph was plotted, we can see that except for angle of scattering 0, for all other figures there are two peaks, and these two peaks correspond to original wavelength lambda and the increased wavelength lambda dash. And we observe that as the angle of scattering increases, the distance between the two peaks, which is equal to the Compton shift, it also increases. Now, classical mechanics failed to explain the phenomena of Compton effect. According to classical mechanics, the scattered radiation should consist of only one wavelength. There should not be two wavelengths. And hence, classical mechanics could not explain the presence of the higher wavelength lambda dash in the scattered radiation, or the Compton shift could not be explained classically. So we now take the quantum mechanical approach to study the Compton effect. Certain assumptions are made here, and the first is that the incident X-ray radiation consists of large number of photons, and if nu is the frequency of X-ray, incident X-ray, then energy of each photon is given by E is equal to h nu, and the momentum of photon is given by h upon lambda or h nu upon c. See, the energy can also be given by E is equal to hc upon lambda, because we know the relation that wavelength into frequency is equal to speed of light. Now in this particular relation, momentum is equal to h upon lambda. We have substituted, or we can substitute lambda is equal to c by nu to obtain this relation. Second assumption is that the target element consists of large number of electrons which are free electrons and they are initially at rest. The third assumption is that when the X-rays fall on the target material, the photons which have particle nature interact with the free electrons which also have a particle nature. Therefore, the photons get scattered at a certain scattering angle theta, and in this process, the electron recoils through an angle phi. So, in this particular figure, the photons, X-ray photons or beam of X-ray is incident on target material. Energy of photon is given by E is equal to h nu, and this can also be written as E is equal to h nu is equal to hc upon lambda. momentum of photon is given by, I have stated it initially that it is given by h upon lambda. But if I use that lambda is equal to c by nu, I can write momentum of photon is equal to h nu upon c. For the free electron, it is at rest, so its momentum is 0, while its energy is purely the rest mass energy, and it is given by E is equal to m0 c square, where m0 is the rest mass of the free electron. Now, the incident X-ray photon is scattered through an angle theta. So, this is the scattered photon and its frequency or energy has changed. So, if its frequency after being scattered is nu dash, its energy will be given by E is equal to h nu dash. This can also be written as E is equal to h c upon lambda dash. Now, the relation I have used here is nu dash into lambda dash is equal to c, and its momentum is given by h nu dash upon c. See, initial frequency was nu, scattered frequency of the photon is nu dash. Now, what about the recoiled electron? It is a relativistic particle and its energy is given by E is equal to under root of m0 square c raised to the power 4 plus p square c square, and its momentum is taken to be small p. Now let's see what happens before the collision. Before the collision, if you look for these parameters before the collision, the energy of the photon is h nu, and using the relation frequency into wavelength is equal to c, this energy can be written as hc upon lambda. Momentum of the photon is given by h upon lambda. Now, this is the consequence. How I have written this momentum of photon is equal to h upon lambda. We will see it in our next lectures. This is the consequence of wave-particle duality. In wave-particle duality, momentum is equal to h upon lambda. Now here nu is the frequency and lambda is the wavelength of incident X-rays. Now in case of free electron, it has got energy which is its rest mass energy. Remember, we have taken this before the collision, and since it is at rest, its momentum is 0. Now see the parameters energy and momentum of scattered photon and recoiled electron after the collision. Now after the collision, energy of the scattered photon is given by h nu dash, and I have mentioned we can write this as hc upon lambda dash by using the relation that frequency into wavelength is equal to speed of light, and momentum of the scattered photon is h upon lambda dash. Now here nu dash is the frequency and lambda dash is the wavelength of the scattered X-ray photon, and energy of the recoiled electron is m0 square c raised to the power 4 plus p square c square within the under root sign. Here m0 is the rest mass of the free electron, and we have taken that the momentum of the recoiled electron is suppose p. Now the collision between the incident photon and free electron is perfectly elastic, and whenever there is a elastic collision, then both energy and momentum of the particle before the collision and after the collision remains same. That is, the energy and momentum before and after the collision are conserved. So by law of conservation of energy, the energy before the collision should be equal to energy after the collision. So if we write before the collision, it will be the sum of energy of the incident X-ray photon plus energy of the free electron which is at rest. So this sum, it represents the energy before collision, and energy after the collision is the sum of energy of the scattered photon plus energy of the recoiled electron. Now, if you make the rearrangement, then in this case we get this under root of m0 square c raised to the power 4 plus p square c square. It is equal to hc upon lambda minus hc upon lambda dash. I have taken this term here plus m0 c square. Squaring both the sides. So if I square both the sides, I get m0 square c raised to the power 4 plus p square c square is equal to square of the bracket hc upon lambda minus hc upon lambda dash plus 2 times bracket hc upon lambda minus hc upon lambda dash m0 c square plus m0 square c raised to the power 4. I used the simple relation a plus b square is equal to a square plus twice ab plus b square. And if you make the rearrangement, if you observe this term m0 whole square c raised to the power 4 will get cancelled with this term, and if you make the rearrangement after taking out c square common, then you get the equation 1, that is p square is equal to h upon lambda minus h upon lambda dash whole square plus twice m0 c h upon lambda minus h upon lambda dash. Now, this was according to law of conservation of energy. If we apply the law of conservation of momentum, then we have to take the law of conservation of momentum along the x-axis and along the y-axis. So for law of conservation of momentum along the x-axis, if you observe this particular figure, then we see that this is the direction of scattered photon, this is the direction of recoiled electron. Here it should be P. Instead of theta, it should be P. So, to find the components of the momentum, this is the momentum of the scattered photon. To find the component of momentum along the x-axis, what I have done? See, I am using this particular figure. Here if r is a vector, then its component along the x-axis will be r cos theta, and its component along the y-axis will be r sin theta. So I am using the same concept here. The scattering angle is theta. This is the momentum of the scattered photon. So the component of this momentum h upon lambda dash along the x-axis will be h upon lambda dash cos of theta, and its component along the y-axis will be h upon lambda dash sin of theta. By using this concept, by using this figure. Now, in this case, the electron recoils along this direction. It is having momentum p. And remember that this angle phi, it is in a negative direction. It is a negative angle. So, its component along the x-axis will be p cos of phi. P actually it is p cos of minus phi. but cos of minus phi is equal to cos phi. And its component along the y-axis will be p sine of minus phi, but sine of minus phi will be minus sine of phi. So its component along y-axis is minus sine of phi. So let's go back to our initial slide. Now in this I see the component along the x-axis. So along the x-axis, the incident photon was traveling along the x direction and its momentum is h upon lambda plus the momentum of the free electron which was at rest, it is 0. So this gives me the total momentum before collision along x-axis. What about the momentum along x-axis after collision? It will be sum of momentum component of the scattered photon along x-axis plus the momentum component of the electron, recoiled electron along the x-axis. So these two terms are coming here. If you make the arrangement, we get equation 2. P cos of phi, it is equal to h upon lambda minus h upon lambda dash cos of theta. This is our equation 2. Now we will write the components of momentum along y-axis. So along y-axis for scattered photon the momentum was h upon lambda dash sin theta. But for recoiled electron it is minus p sine of phi. And see, conservation of momentum along y-axis. The incident photon was traveling along x-axis. So its component along y-axis is 0. Free electron, it was at rest. Its component is again 0. So we get 0 plus 0 before collision. It is equal to the component of momentum for scattered photon along y-axis plus component of momentum for recoiled electron along the y-axis. Now here, once again, observe that the angle phi of the recoiled electron, direction of recoiled electron is negative and cos of negative angle is cos phi, cos sine of minus phi will be minus sine of phi. This is the relations I have used here. Now if you make the arrangement, we get p sine of phi is equal to h upon lambda dash sine of theta. Now squaring and adding equation 2 and 3. So if you square and add the equation 2 and 3, we get its simple term here. Now this particular term is obtained by expansion of that equation 2. So if you observe p cos phi square plus p sin square phi, it gives you p square. Cos square phi plus sin square phi is equal to 1. This is equal to h upon lambda whole square minus twice h square lambda lambda dash cos of theta plus h square upon lambda dash whole square. Now adding and subtracting the term 2 into h square upon lambda lambda dash in our previous equation. So here I have added and subtracted, and if I make the necessary rearrangement, I have rearranged this term. This minus term I have taken within these two terms. And if I rewrite this equation, I get p square is equal to h upon lambda minus h upon lambda dash whole square plus twice h square upon lambda lambda dash 1 minus cos of theta. Now, how did I get this term? simply by using the term A minus B square is equal to A square minus twice AB plus B square. This whole term reduces to this bracket square. And here, by taking out these common terms, I get the second term. Now, equating our equation number 1 and 4, both for P square. So, if we equate these terms and you make the necessary rearrangement, whatever is cancelled here, this term gets cancelled with this term, and if you make the necessary rearrangement, then you get finally m0 into c. m0 into c, 1 by lambda minus 1 upon lambda dash. This is equal to h upon lambda lambda dash 1 minus cos of theta. 2h. Here 2h gets cancelled with here 2h. And finally, this term, cross multiply this and solve this term. You can write Compton shift delta lambda is equal to lambda dash minus lambda. This is equal to h upon m0 into c, 1 minus cos of theta. So, from equation 5, we observe that this angle theta is the angle of scattering of the photon, and this Compton shift delta lambda depends only on the scattering angle. Rest of the terms are constant. All other terms are constant. Thus, by quantum mechanical approach, we can explain the Compton shift and the presence of higher wavelength lambda dash in the scattered X-rays. And we can observe that the Compton shift was independent of the nature of scattering material and the incident wavelength. It only depends on the scattering angle theta. Now let's see some cases about the Compton effect through different angle of scattering. What happens if the angle of scattering theta is equal to 0 degree? In that case, cos theta means cos 0 is equal to 1, and Compton shift becomes equal to 0. This cos theta becomes equal to 1. So 1 minus 1, 0. So Compton shift becomes equal to 0, and that was what we observed in the graph. For scattering angle theta is equal to 0 degree, there were no two peaks, only one peak was observed, meaning the Compton shift is 0. This is the smallest value for the minimum value of Compton shift, and it occurs for angle of scattering theta is equal to 0 degree. Case 2, if the incident photons, X-ray photons, are scattered at an angle of 90 degrees. In that case, we know cos 90 is equal to 0. Hence, Compton shift is given by delta lambda is equal to h upon m0 into c. Now here, the rest mass of electron is 9.1 10 raised to the power minus 31 kg. Speed of light 3 into 10 raised to the power 8 meter per second. And the Planck's constant, here it should be small h. The Planck's constant is 6.62 10 raised to the power minus 34 joule second. If you substitute these values, then the Compton shift comes out to be 0.0242 into 10 raised to the power minus 10 meter, and we know that 10 raised to the power minus 10 meter is 1 angstrom. So, Compton shift delta lambda at a scattering angle of 90 degrees is equal to 0.0242 angstrom. When the incident X-ray photons are scattered at a scattering angle of 90 degrees, and the Compton shift so produced is called Compton wavelength, and Compton wavelength is having the value 0.0242 angstrom. Case 3, If the angle of scattering is 180 degree, in that case cos 180 is minus 1, and Compton shift it becomes equal to twice h upon m0 into c. If you put the values, this value comes out to be 0.0484 angstrom. This is the maximum Compton shift that can be produced, and it occurs for an scattering angle of theta is equal to 180 degrees. Thus, quantum mechanics can successfully explain the Compton effect, the presence of higher wavelength in the scattered radiation, and the Compton shift. On the basis of all this is done on the basis of quantum theory, where the incident X-ray was supposed to be made up of or consist of large number of particles called photons, and each photon behaved like a particle. So that's all about the Compton effect. Have a nice day.